Hey folks, this video is going to be about the two mechanics FRQ practice that were specifically for the AP test and the types of questions that are going to show up on the AP test. So what I want to do is, because I'm posting this early, I'm going to start with just some hints and ideas for them so that if you're just kind of stuck on the problem, you can start with maybe some push in the right direction, and then you can pause the video after that and wait until later to watch the full solution so you get a chance to work through it on your own. So I will go ahead and do that first, and then we'll move on. All right, so this is the dart problem where a force is exerted on a dart in the horizontal direction moving through a tube of length L. After it exits, it collides with a mass M, and it passes through the block, which exerts a retarding force F on the dart. The dart then exits the block with a speed VE. So part A is asking you, they're experimenting with a variety of different tubes. Assuming air resistance is negligible and all of their parts remain the same, should they use a long, a short, to make the exit velocity the largest? Justify your answer. For this one, I would consider what's going on with the force applied to this dart while it's in the tube, and why would it matter? So it's going to be the same force, a constant force no matter what. If the force stays the same, does it matter whether it's longer, shorter? What's the result going to be? If you apply a constant force for a longer distance, what's going to happen when it comes out? If you apply a constant force for a shorter distance, what's going to happen when it comes out? And remember, we're thinking in terms of velocity. So how does the force applied affect the velocity of the object? Okay, part B. Clue for this one, or hint for this one, derive the following equation without algebraic manipulation. Explain whether it matches your explanation. The key here is, I would say, pay attention to the direction of the forces. The variables here do match up exactly with the things in the problem statement, so make sure you think about what direction each force is going and whether this matches up with your answer based on that. Okay, part C. Explain how the students could use the equation to find the launch speed of the dart if the time in the dart was 2 seconds. For this one, obviously, well, the straightforward thing is we can put in 2 and we can find the force. So force is 10 times 2. So if you can find the force, how does force help you find speed or velocity? Very similar question to part A in the sense that if we know a force, how does that force impact the velocity of the dart? And this time it's the launch velocity coming right out of the tube. How does the force affect that? So again, the link between force and motion is important for these. Predict what will happen to the launch velocity if the tube is changed so that the time is doubled. There's a couple ways. My hint here is there's a couple ways you can go about this. There's a couple different equations that talk about velocity and time and can be linked back to force. So that we've went through one of those in our momentum unit. There's an equation that talks about some time and velocity and force. And there's also stuff from earlier on, like in our kinematics unit, that talks about time and velocity and can also be linked back to force, though not quite as directly as the one from momentum. So there's a couple ways you could think about that one. But yeah, I'll go through my preference when we do the answer. E, yeah, I think the main hint I would give here on E, think about how this, especially this 5t squared, what is that, does it connect back to any of the other equations or things we've seen earlier in this problem? And how does it connect to that? Your equation sheet will actually be a big help here. I mean, it'll be a big help on all parts, but especially here, once you recognize a link, and it took me a little while, but once you recognize a link between this 5t squared and something we saw before in this problem, it'll help you out a lot in figuring out what this equation actually is. This is an equation we've seen before. This is something that we went over in one of our units. So those are the hints for that one. For this one, this is the lab one. So students are performing an experiment to determine rotational inertia of a T-shaped PVC apparatus in the lab using the setup shown. And they're going to plot their data in a graph. They have equipment found in a high school laboratory, but they must use the setup with this T-shaped PVC apparatus rotating on a ring stand, accelerated by a hanging mass. Okay, briefly identify each quantity to be measured. So here, think about what we could measure here, right? So we've got a mass and it's going to be moving. There's going to be forces acting. There's going to be some accelerations. We're going to be having both a vertical motion here and a rotational or circular motion as this is rotating around. We'll call it rotational motion, I guess, rather than circular. Rotational motion for the PVC. So based off that, what could we measure? So you can edit your answer as you go on and say, okay, maybe we don't need to measure all these things, but it might help to list all the things you could measure first. That'd be my hint. Briefly describe the procedure used to determine. So this is just process, right? We all know from looking at this, okay, you're gonna have to drop the mass falls, it pulls on the string turns, and this rotates. So you have to do that, but as you're doing that, what do you have to do to get these quantities that you want to measure as you're going through that procedure? So like, okay, make sure you hold this ruler here or this photo gate or any of the other types of things that we've used before and that would be available in a physics lab to measure things like velocities or forces or times or distances. What quantities calculated could be graphed on the horizontal and vertical axes? Look on your equation sheets. Every time it asks you about the graph, if we're finding I, we're going to plot I, there is some equation somewhere, some relationship between multiple variables that will get you I. And very likely, that's going to be something on your equation sheet. Something like, for example, if I were asked F equals ma, right? If I could find force and I could find acceleration, I could do some graphing and we could find mass because there is a relationship between those three variables. And if I find two of them, I can find the other. So look at your equations, think about what kind of a graph you could make based off an equation that has I in it somewhere, the rotational inertia or the moment of inertia. Describe what information from the graph would be used and how it would be used. So again, this is just going into detail and saying, because this equation relates this and this to rotational inertia, I can graph this versus this and the slope of it, or whatever it is that you end up doing, something from your graph. Usually the slope is going to be the preferable one, because if you can graph like force versus acceleration, you can get a slope of your mass, etc. Okay. Students calculate the torque from the string and the angular acceleration. They notice a non-zero vertical intercept. What is the physical meaning? Okay, so think about if you require a non-zero torque, that's your vertical, right? Torque versus acceleration. It's saying it requires a non-zero torque. It has to start above zero in order to get some acceleration. What does that mean for this? How can you explain that using this? Why do you need above zero, a positive torque in order to cause some acceleration here? Okay, so that's it for like the tips and hints. So you can certainly stop the video there if you just wanted to get some extra ideas for working on it. Now, I will also go through and try and do a full solution. The caveat here is there is no full solution listed. So I think I've got it. It took me a little while to look through these and figure it out. And take that hopefully as a confidence boost that even your physics teacher, these problems are tough. They took me a while to figure out. But I think I got there. Okay, so I'm going to go ahead and walk through each one. All right, so for this one, air resistance is negligible. All other parts of the experiment remain the same. Now, there might be friction in the tube, but even if there is friction in the tube, that's not going to get bigger or smaller. Friction only depends on the normal force. So if the mass is resting inside the tube, the dart, and it's got a normal force due to gravity pushing down and the normal force up from the bottom of the tube, that's going to stay the same. Friction's not going to change at all. So even if there is friction in there, it doesn't matter. The question is just, if we have a constant force and we want it to go faster when it comes out of this block. Now notice we're not changing anything about what happens inside here. There's just this retarding force F it's going to push back on it, right? It's just going to push against it, whatever that force is. And ideally, we would want it to be moving faster when it hits so that it'll be going faster when it comes out. So really, we're just trying to maximize this. Another way to say this question, I think we're just trying to maximize the exit velocity out of the tube so that we can also maximize the exit velocity out of the block. Now, thinking about that in terms of length, if we apply a constant force over a longer distance, right, the force is constant, the acceleration is going to be constant because we're not changing the mass. F equals ma, Newton's second law, says that because we have a constant force applied and a constant mass, we'll have a constant acceleration. We would like to have that constant acceleration be experienced by the dart for a longer period of time, so it has more time, more distance to accelerate and reach a higher velocity upon exit. So a longer tube would be preferable so that we can have the dart accelerate over a longer distance while the force is applied to it within the tube and thus exit with a higher velocity. So that should be your justification, is a longer tube. And you could use an equation to justify that. You could go right over to your kinematics equations, zoom in a bit here. You could say, so I know that my initial velocity is 0, or here, down here even better, my initial velocity is 0, and my acceleration is constant. I want to have a longer distance, a longer displacement during which I experience that acceleration so that I get a higher exit velocity. Okay, back to the problem. B, they derived this equation. Does this make sense? So we said longer tube is better. And my hint for this was, look at the directions of the forces. This F, big F, exerted on the dart while it's in the tube, that's a positive force going to the right. We'll call to the right positive. Seems to make sense here. The retarding force F resisting the motion of the dart as it passes through the block, that little f is negative. It's going back to the left. It's opposing the motion, trying to slow it down as it goes through the block. So, big F is positive, little f is negative. We said if you make a really big length of tube, the longer tube, longer L, that should result in a higher exit velocity out of the block. So if this is a positive number and we really make this L big, this is going to be a big positive number. This is a negative force. X, the width of the block, doesn't change. This is a set value, 2fx. So if we make this L really big, then we've got a big positive number, a smaller negative number, and overall this is going to increase. So yes, it matches up, because with this being a positive, this being a negative, making this L bigger is going to also make VE bigger. So we didn't manipulate the equation, we just looked at it and said, okay, based off this, we know this is negative, this is positive. If we make this bigger, we're good to go. Okay. Part C, explain how the students could use the equation above to find the launch speed. Okay, so we said this is fairly easy to find force, right? Time is 2 seconds, 10 times 2, force is 20 newtons. Fair enough. Now, if we know the mass, m, of the dart, how can we use this force to get to a velocity? Well, our link between force and motion is always, or has pretty much always been, and is the best way to go about it is Newton's second law. It's fairly simple, right? Force equals mass times acceleration. So our 20 Newton force, whatever the mass is, if we take the force divided by mass, that'll give us our acceleration. Alienware updates. All right, that'll give us our acceleration. And we can use that acceleration to find the launch speed of the dart. Okay. So that would just be kinematics equations, by the way. So part C, use Newton's second law, and then you can go into kinematics equations using the acceleration and the time to find the velocity. D, predict what would happen to the launch velocity if the tube same time t is doubled. Okay, we said that the length of the tube, we've got a constant force, right? Constant acceleration. So if we go over and look at this, again, back to our equations here, what's going to happen to the exit velocity if the length is increased so that the time is doubled. If we double the time, let's look at this one. So if we double the time, this displacement is going to quadruple. So in this equation, if we moved xo over here and said displacement equals initial velocity, that's 0. I think we've established that. But even if it's not 0, it's a constant value. So if we, I think it is 0 in our case though. So if we double this time, anyways, we know our acceleration is constant. So if we double t, that should quadruple this displacement because we've got t squared. Now, if we quadruple the displacement, what happens to the exit velocity? Here, actually, let's see. Let's go back. 1/2 axt. Just want to make sure I'm using the right equation here. All right, the launch velocity of the dart if the length of the tube is changed, the time t is doubled. Okay, I think I was using, okay, a tip here also, just real quick, don't be afraid to look at the other answers. So here, they're telling you that this is an equation you want to match up with this. So according to this, if we peek at this equation, look ahead, the velocity should, when time is doubled in this equation, if we double t, that's going to quadruple the velocity. So according to their answer, if time is doubled, we should quadruple it. Of course, you can't just put that down. You have to justify it. But we can use that to look back and say, okay, what could we look at to figure out if time t is doubled, it quadruples our exit velocity. All right, let's go back to here. Okay, so we could use some kinematic stuff, right? And that's not bad. We can also use some super cool, where is it? Ah, here we go. Okay, so in our momentum unit, and this is a tricky one. This part really, it took me a while to catch on that this is what they were going for. If you look at this equation, where'd it go? Not that one. This one. It's got a 5t squared in it, and that on the surface, right, it looks kind of like, okay, whatever, it's 5t squared, who cares? If we look at the previous equations we were given here, 10t, as a calc-based physics student, hopefully we should be thinking about integrals and derivatives. It turns out if we take the integral of 10t, this equation, so integral of force with respect to time, integrate this, we would get 5t squared. Interesting. Okay. What about the integral of force with respect to time? Does that show up anywhere? Oh my goodness. Unbelievable. It does. So this goes back to our momentum unit. The impulse J, which impulse is just, a simple description is force times time, force times the time interval, but the way to do it in terms of integration, impulse is the integral of force with respect to time. It's also equal to the change in momentum. That's our momentum impulse theorem, which you probably would have somewhere in your notes. So don't forget about that one. It's a really important equation. It's just a rewriting of Newton's second law of motion. We went over that in our momentum unit. But so the impulse is the integral of force with respect to time, and that's equal to the change in momentum. And if we go back here, where'd it go? Here. That's really what they're doing. So if this is the integral of force with respect to time, which it is, we integrate 10t and we get 5t squared. If we took that m and multiplied it over here, we'd get mv, mass times velocity. That is just our momentum. So this is the momentum impulse theorem. Mass times velocity is momentum. 5t squared is the integral of force with respect to time. We integrate this with respect to t, and that is J, our impulse. So this is going back to the momentum stuff. Now, this is where it's very useful to at least glance at each part so you can see, is there anything that will help me from this going back to D? Because part E actually helps us with D. So you could say, okay, I predict that based off the momentum impulse theorem, if I take the integral of this, right, integrate force with respect to time, I get 5t squared, okay? And according to the momentum impulse theorem, that impulse, which is the integral of force with respect to time, is equal to the change in momentum. So if I've got that mv, right, so our initial momentum was 0. So that doesn't factor into it at all. We would, to do change in momentum, we'd technically do final momentum minus initial, but we started at rest. So we're just looking at the final momentum. So that final momentum, mv, is equal to the impulse, which is the integral of force with respect to time, to 5t squared. So based off that, and the fact that we can integrate this and use momentum impulse theorem, we can justify our answer by saying, according to momentum impulse theorem / Newton's second law of motion, if we integrate this force with respect to time to get impulse and set it equal to the change in momentum, then therefore the velocity, which, like it says down here, the velocity is going to quadruple when the time doubles. So you don't have to, again, without algebraic manipulation of equations, make sure it matches your explanation. And you could just say, hey, look, this is momentum impulse theorem. 5t squared, that's the integral of force with respect to time. We're integrating this. M times v, that's velocity. So, yeah, there it is. Okay, that is the DART problem. If you have any more questions, certainly email me. Let's tackle the experimental one. Okay, this one is setting up an experiment. Now, briefly identify the quantities to be measured. Again, I think it's very useful here to think about what are all the things we could measure. We could measure mass, right? We could put some masses. It's also important, we could vary the masses, right? We could put heavy masses, we could put light masses on here, either way. So we could measure and know the value of different masses that we put on. We could also measure, we could potentially measure linear velocity, right? We could try and see like, okay, how fast is it going at a certain point? It'd be hard to measure linear velocity all the way down because, as we know with our photo gates, you could hold it at some point, it would pass through and it would measure the velocity there, but to do that at every single point, well, you'd need a lot of photo gates. You might be able to do that. We can measure time, figure out how long it takes to go down, right? So we could do time, we could do distance, the height, right, above the table. We could maybe do some things with angular velocity. So we know that angular velocity omega is vt over r. So we can use the radius, which we can measure, right? That's another thing we can measure, the radius of this rotating object, right? And we could use a photo gate, stick it under here and measure as it goes by, right? We'd get that tangential velocity. Every time that this wing goes by through the photo gate, we'd get a tangential velocity. We could use that with r, we could get omega. So we're starting to get all kinds of things we could measure. So I would almost gather just a list of things you could, then progress through, decide how everything is going to end up working out, and then go back and make sure that everything's good for A with all the things you actually want to measure. So again, things like mass, height, time it takes to go down, radius of this, even the radius of this little, it will be important, the radius of this little circular cross section, this tube here. Okay, awesome. So we have equipment we can use, right? Meter sticks or some measurement for height, stopwatches or iPhones for for time, and we can use photo gates if those are available for. And I guess that's right. Like, okay, this says commonly found in a high school physics laboratory. Some physics laboratories don't have photo gates. That may or may not be. So you may want to wait on that and see how things work out. But there's a lot of different things we could measure based on our WAS equipment. Okay, briefly describe the procedure to be used to determine the rotational inertia. Okay, so now we actually have to figure out what are we going to do in order to get this rotational inertia. Now, this is where I would start, even here, I would start looking back at your equations. And your equation sheet is going to be helpful because we're looking for equations that have I in them. Okay, got to find something that has I. Well, that has I, but I don't know that that's going to be helpful for graphing. We're looking for something, again, like this. This doesn't have I in it, but if we could do P, we could graph P versus V, and the slope of it would be F, something nice like that. That's a really nice, a nice thing to set up. So that doesn't have I. Now this one, sum of torques, and this is a weird rearranged Newton's second law. If we go back to this, got a table. All right, so this is like that mechanics review, the multi-page thing on Schoology. It's got a neat table that, like we made, that links linear and angular. Where is it? Here we go. So F equals ma, that's Newton's second law for linear motion. Newton's second law for angular motion, torque, or sum of torques, equals I, the moment of inertia, times angular acceleration. Now we're getting somewhere. Okay. So if we can get torque and angular acceleration, we could graph those and we could look at I. That might be cool. Let's see if we can do that. Okay, but how are we going to use a procedure to measure torque and measure angular acceleration? Okay, let's look at torque first. So if we look at a cross-sectional view, which I have conveniently drawn, here's a top-down view of that circular piece that's rotating. So again, that's that like central column. Oops, that central column right here that's got the string tied around it. So that's what's going to be pulled on by the string. The string is going to pull on the outside of that, and it's going to cause it to rotate. So here's the green is like my string, right, pulling on it. And then we've got a torque because this is the very center of that, the center of the object's rotation. And there's a little radius r here, which is the cross-sectional radius of that little middle piece, the middle column. And then the force from the string is pulling on it, and it's going to cause it to rotate. That's our torque. Of course, torque is just the force times the radius. We know that from our equations. All right, so that's how we could find torque. If we can get the force that's applied here, right, and then we can get this radius. The radius easy enough to measure. We could measure that, or find it by circumference and using some geometry. We're able to get there. All right, that's simple enough. The force is a little more interesting. Now, we need to consider the fact that, okay, we're pulling, I'm gonna go back to this. So we're pulling on that, the string is pulling to cause this to rotate. We might be tempted to say that the force is just equal to the force of gravity, which would be mass of this object times the acceleration of gravity, mass times 9.8. The problem with that is the only force acting is not, for this object, right? It's not in free fall. If it were in free fall, the only force acting would be the force of gravity, right? 9.8 meters per second squared times this mass, and it would fall at a certain acceleration, with a certain acceleration, 9.8 meters per second squared, minus air resistance. But in this case, we have tension in the string that's pulling back on it. So if we're going to find the net force, right, there's a net or total force that's pulling down and therefore is pulling on this and causing it to rotate. But that force isn't just based on the force of gravity. I'm going to draw a little equation here. So let's do color, brushes. Okay. So the force net, or the net force, my beautiful drawing skills here. Okay, so net force, right? It's going to equal force of gravity, which is pulling in the, I guess we could call it the positive direction, downwards, or which downwards translates to pulling to cause this to rotate, right? Pulling on the string, unwinding the string, causing it to rotate. So that's positive force, and then we're going to subtract off the force of tension. Okay. So if we can find the, we know the force of gravity, that's simple enough. If we know the mass, right? So if the mass is 1 kilogram, we can get the force of gravity, easy enough, no problemo. All right, but how can we get the net force? Well, we know that net force, right? Net force, oh boy, drawing. Okay, net force must be equal to a mass times the resulting acceleration. So this acceleration is not going to be 9.8. It's going to be whatever acceleration our block or our mass actually accelerates with as it goes down. So we have an equation for that. So we know the mass. If we could just find the actual acceleration of our mass as it falls, that would be great. Now, can we do that? I think we can. Let's look back at our kinematics equations. We can find acceleration easily enough. I mean, here we go. We're starting from rest, right? This is 0. And this one's unhelpful because we don't know the final velocity. Maybe you could get it with a photo gate. Let's keep looking. So this one has displacement, right? Displacement, initial velocity we know is 0, releasing from rest. There's acceleration, there's time. So all we have to do for this, to use this equation, measure the time it takes for the object to go however far, like maybe to the floor or almost to the floor. So we can measure time. And the height, or the displacement that it took to go that. We know that it's released from rest, so we don't have to worry about that. That would get us the acceleration. We'd have to change it to y, right? Acceleration in the y direction, but that would do it. So we can measure the height, or displacement. We can measure the time, and then use the second kinematics equation to find the actual acceleration of this object as it goes down. Great, so we can do that. We can measure those. So your procedure now would look like, okay, you're gonna have to drop this, right? You're gonna have to measure the height or know the height. You're gonna have to measure the times, how long it takes to go down, but you can get that acceleration from that. And every time you do, once you get that acceleration, you can find the net force experienced. And now we can go back and say, okay, we know the net force. That net force is gonna provide our torque. And torque is just weird torque symbol. Torque is just the force times the radius, technically times sine theta, but these are at a right angle. We don't have to worry about that. So once we know the radius of this little middle cylinder, middle column thing, we know that R, and then we know that net force here that we found from mass times acceleration, we're good to go. We can find the torque. Okay, that's one. Again, going back to these, where'd it go? I was on this one. Okay, there's our equation that we want to use. Torque equals moment of inertia times acceleration. Great, we're getting there. Now we just need angular acceleration. But wait, this is awesome. We found the linear acceleration using this. Well, not using this, but we found the linear acceleration using our kinematics equations. So if you measure that height, right, and you measure the, the time it takes to go down, your angular acceleration, going back to this linking table, where'd it go? Angular acceleration. I guess they don't have the equation up here, but you can just say, I'll write it over here. So angular acceleration, alpha, is just linear acceleration, a, divided by, now, this we have to be a little careful. We want this alpha, right? We want this alpha for, where'd it go? Okay, for this. Now, there's a couple ways we could do this. Technically, if you were able to count the number of rotations, right? You could count the number of times that this lever arm or this big thing rotates around and say, okay, it went around 5 3/4 times or something like that, right? And you could figure out the circumference that's swept out by the outside of it, and you could use that. So you could do that, but it's going to be easier for us to use our linear acceleration, from this. So yes, we could go through and find the, although now we're talking about these arms, so we probably would want to. So what we want to do is find some way to get the acceleration, right, of this upper part. Because really what we care about is the angular acceleration of this object. So we should be able to get that. Although, actually, no, that's fine. I was thinking we had to do it for the whole thing. As you can see, I'm still working out kinks in this. But no, we would just have to do it for the middle, right? So however fast or however much this whole thing is accelerating and spinning, the middle part is going to be accelerating and spinning at the same rate, right? It's not going to, a point on this is not going to go around in a circle more times than this outer point. They're going to rotate at the same rate. So we can just use our previous values. So we can just use the A that we got from our kinematics equation that we just used. And we can use the R, this little radius here for this guy. That'll be totally sufficient to get us alpha, which is awesome. We don't really have to do a whole lot more work. So really all you have to measure is the distance, right, height from the top to the bottom of the table, or from this starting point to wherever you're stopping, the time it takes to do that, then use your kinematics equations to get acceleration, linear acceleration A, use Newton's second law to get net force. That'll give you torque times the radius. And then again, use alpha equals A divided by R. That'll get you your angular acceleration, and you are good to go to start setting up your T equals I times A. Now this will be a nice graph, right? We've got a Y axis, an X axis, and then our slope. However, if we just drop, and this kind of gets into part C. So which quantities calculated from measurements in part B should be graphed on the horizontal and vertical axes? Great, well, we've determined so far. Okay, I think we want torque and acceleration. So torque on the y-axis, angular acceleration alpha on the x-axis. Great, everything's cool. Explain how you would use measurements. Now this part, right? Explain how you would actually get, actually, oh no, that's part D. We haven't gotten there yet. Explain how you would use your measurements to calculate the quantities. Yeah, so this is where you would, we kind of already went into this. I kind of already jumped on that. But yeah, we would use the height and the time and the radius using the process we just described with kinematics, with Newton's second law, making sure we get angular acceleration alpha, and then we could calculate the torque and the angular acceleration. Also, keep your eyes open, right? Look ahead. If you want to read through the whole problem, you'll get some hints. Look at that. There's torque and angular acceleration alpha showing up later. It's not a coincidence. All right, D, describe what information from the graph described in part D would be used and how it would be used to determine. Okay, this is where it gets a little weird, and I kind of got caught up on this for a little while. I'm going to actually do a new paint because I'm out of space. Don't save. Maybe I should have. Whatever. All right. Here's our graph. Really straight lines on our graph. We said we want alpha on the x-axis. We said we want torque on the y-axis. Okay. If we make our measurements and do our calculations and everything is great, but we use one certain mass and one certain height, it should probably take just about the same time to get down every time. The same radius, right? We'll measure the same radius. So what we would get if we just, even if we repeated this 10 times to try and be thorough, we'd probably get something that looked like this. So like pretty much everything in the same exact spot. And that's not great for graphing. I mean, you maybe could do that with some computer assisted stuff and do a best fit line. But that's not ideal because if we keep the mass the same, right, we're probably just going to have the same torque every time, and based on the same torque, our moment of inertia I probably isn't going to change, so it's not going to change unless we add some mass or move the mass around on the outsides of it, which in theory we could well, it doesn't look like these are adjustable, we can't move them in. So it kind of looks like a bit of a problem. However, how could we get some other spots on here with a different torque and like a different angular acceleration? Well, looking at our picture, we said that the torque depends on the force, right? And the force is going to depend on the mass and the acceleration. So if we change this mass, right, we put a lighter mass on it, a heavier mass on it, that should change it. I mean, we could do this qualitatively too. If we put a really heavy mass on and let it go, it's going to start whipping that thing around. If we put a really, really light mass on and it barely gets going, it's like barely starting to turn, it's going to take a long time to get down here, right? it's going to take a long time to fall. So we could vary the masses. So get your mass, your set of masses out in your classroom and make sure you vary the masses. You could, you might have to go back and edit your descriptions, right? Like, oh, the procedure, you also need to vary the masses because we're going to need that when we do graphing. The reason for that is we want different points, right? We don't want just that one point in the middle. So now you've got a graph that looks like, I'm trying to draw something reasonable here, something like this. Okay, something like that. So, and then you can do a fit line, be something like, I don't know, whatever it might be. So you've got your different torques with different masses and your different angular accelerations, and then you can get your slope of that line, right? Then it's actually a nice graph. So you've got torque versus angular acceleration, and this is like smaller masses, right? Smaller masses, less torque, less angular acceleration. Bigger masses, more torque, more angular acceleration. We're going to go faster. It's going to spin super fast. But the slope of this line should be your I that you wanted to get in the first place. Just, again, based off this equation, torque or sum of torques equals I times alpha. All right. So there we go. We could use that, how it would be used to determine. So we look at the graph, make sure we use different masses. We get torque on the y-axis, alpha on the x-axis, and we are golden. Part E. Students calculate the torque from the string and the angular acceleration. Imagine that. Well, why would we ever do that? Of the PVC from each data point. Okay, so then they graph torque versus alpha, but what they notice, which I have very cleverly, intentionally done, is there is a non-zero vertical intercept. What's this all about? How can we explain and justify, which is what they're asking us to do, or just say, what is the physical meaning of this intercept? Why on the graph would there be a non-zero or a positive y-intercept? It says non-zero, but I have deduced that it also should be positive. Anyways, that's another thing. But what is the physical meaning? So let's think about this. If we have, where am I going? Let's go back here. So we said the torque depends on the mass, right? Bigger mass, bigger torque. Can you put a mass that has a torque of 0 on there? Well, we'd have to put like nothing on there, right? Or another way to think about this is, can you accelerate your object with a torque of 0? Well, no, we can't accelerate it if we put no torque on it. But let's go back to our net force. So we said the net force, which causes our torque, right? So this is very related to the torque, is equal to force of gravity acting downwards minus the force of tension. So again, we've got to account for the fact that yes, gravity's pulling down on the mass, but you could put a mass on that object, right? And you could imagine doing this. So you've got this, again, thinking more qualitatively, you've got this kind of heavy big thing on here. It's made of PVC pipes. If you put one of the tiny, tiny, tiny masses on it, gravity's pulling down on that mass, right? The force of gravity equals that mass times 9.8. But maybe this doesn't move at all. You could foresee a point where you put a little tiny mass on this and it doesn't actually rotate it because of this tension. It's almost like this idea, kind of like our idea of static friction. You have to overcome, you have to get a mass that's big enough, that the force of gravity is big enough to overcome tension to the point that you're actually getting it to move. If you put a really small mass on here, it's probably not going to move. It's got to be big enough of a mass that you get it to move. So this y-intercept means there is a certain minimum required torque, a minimum required amount of mass that you have to put on this object in order to get it to, or on this setup, on this apparatus in order to get it to move and rotate. If you put too small of a mass on there, you can't say, oh, well, if my torque is, here's, maybe this is a torque of 1, and this is a torque of 0.5. So, oh, if I put a torque of 0.5 on it, I can still get it to rotate. It'll be fine. Well, no, you won't. It's not going to work. If you try a torque of 0.5 right down here, you're not going to get any angular acceleration, because even though that torque or that that mass is a mass and it would want to exert a torque on this apparatus, the force of tension is holding it back to the point that your mass is too small. You can't get it to rotate. All right, well, I feel like this has been super long for a video, so hopefully you were able to skip around if you needed to. But yeah, I just kind of wanted to go through these. Again, it took a long time too because there was no solution. I had to kind of figure things out as I went. But hopefully that helps you see how these problems are really, they truly are connected to the things that we've gone over. And the tricky part is just figuring out, where do these different things fit in, right? Where does momentum fit in? Where does forces fit in? Where does my kinematics come in? Which equations am I going to use? And look for those clues and those pieces of information you can pull out from here. We saw the torque and the angular acceleration. On the other one, we saw this integral, right? Integral of that force with respect to time. That kind of led us towards the momentum impulse theorem here. So try and look for those, whatever clues and hints and connections you can make to say, okay, maybe I should use my kinematics equations or Newton's second law or the momentum impulse theorem or things like that. All right, that will be it for this long video. Thanks for watching, y'all.